about the reinforcement learning-based quantum circuit optimization via ZX calculus, and the floor is yours.
Okay, thank you for the introduction. I'll start by hold on. Okay, so basically the motivation and the project. Okay, this work is a continuation of my master thesis that we basically exactly the same, but instead of using graph neural networks, we use convolutional layers. And the main goal is to use a reinforcement learning or either to train a reinforcement learning agent to do quantum circuit optimization with ZX calculus. There is a paper, this nice paper by Corvina et al., which you have this rule selection, right? And then hopefully you'll optimize your ZX diagram. And they use heuristics to guide this rule selection. And this is our ultimate goal of our reinforcement learning agent, to learn this optimal rule selection and then compare or benchmark against the library PyZX. This is the library where all these algorithms are implemented. Okay, so basically what we first did in the beginning was doing several tests. We tried the full reduce algorithm, which we believe is the strongest or one of the strongest algorithms in the library of PyZX. And we ran with either non-Clifford and Clifford circuits. This is all probably things that you know already, but let me walk through it very quickly. And say figures A and C are total gate count and 2-qubit gate count for non-Clifford circuits. And figures B and D are total gate count and 2-qubit count for Clifford circuits. And those are circuits of 10 qubits and up to 400 gates. And for Clifford circuits, we clearly see two regimes, right? So we have the regime of low gates, where, sorry for not saying, but the blue line is the full reduce algorithm plus a gate-based optimizer in the end. The purple line is only the full reduce, and the orange line is only this gate-based optimizer. So you can see that in the beginning, when we have a small amount of gates, the full reduce does not perform very well. And it's not until a certain break-even point that the compression is good. So it reaches a meaningful compression. And that's the strength of the approach, both in the 2-qubit gates and the total gate count. So what we did was, okay, say we'll start by the simple case. Let's focus on the Clifford circuits, and we'll see these two regimes, and we'll try to improve on these two regimes via reinforcement learning. In the first regime, the result of this, as we mentioned, is not really good because you're trying to achieve a compression and you end up with more gates. And in the constant regime, this is also something that you already know, but this is because when we have only Clifford circuits, we always end up with a similar structure in the end up to a certain break-even point, which is this. I don't know if you see my pointer, but it's this circuit that I display here. When you have a certain initial gates, you will always end up in a similar structure with when you have no interior spiders, you only have boundary spiders and certain connections between them. This is not true for non-Clifford. So, okay, what are our rules that we have for the Clifford simplification? And those are local implementation, pivoting, pivot boundary, the identity plus the fusion. This is the full reduce, what it has in its toolkit to simplify Clifford circuits. And we added the rule of reinforcement learning, which is a stop action, which means that the agent is able to stop at any point of the simplification. And this is very useful, as you'll see moving forward. Why do we believe in the beginning we started in this project without knowing anything about ZX, we knew something about reinforcement learning, but not pretty much. So why do we believe in the beginning that this approach in reinforcement learning could yield good results? So basically, we have the full reduce algorithm, or the PyZX algorithm, works applying all possible actions because it prioritizes termination over simplification. As mentioned, once you get to a break-even point, you will have a constant compression. So for Clifford circuits, so it's a good approach, worked well. But at sometimes it's better if you just stopped and not applying all actions. This is the first case that I display here. In here, if you extract the left-hand side diagram, you get 21 gates, and if you apply local complementation to the spider in the middle, it is an extreme case, and you extract the diagram right after it, you will get 35 gates. So in here, in this case, it would be an example of a prejudicial example for the use. And the other thing that not that we notice, but which other could be potential for the reinforcement learning, is selecting interacting vertices. So since the full reduce applies actions iteratively, needs to select non-interacting vertices, because, for example, if you apply local compensation to node 6, it would change the phase of node 7. And then if you had node 7 as a candidate for local compensation, well, in this case, when I apply local compensation, it doesn't matter. But in pivoting or applying 8 to 10 or 8, 9 or 9, 11, it's important which order you do. And if you apply the action in the beginning, maybe we will change the diagram and you won't be able to apply the other actions that you have left. So in this case, our reinforcement learning agent sees the diagram and says, okay, applies one action at a time. So at each step of the process, it sees all the actions and chooses a long one. Okay, so I will explain briefly about reinforcement learning. If you attended the past week, the seminar, you already know pretty much all of it because Max explained it very, very well. But I'll say that in the reinforcement learning is based on Markov decision process. And what does this mean is that you have an environment and the agent interacts with an environment, right? Then the agent takes actions on the environment, and the action that the agent is taking on the environment is the agent only needs information of the present. So it doesn't matter what you did in the past. The agent takes actions only with information they have in the present. And here in the left, I display the typical reinforcement learning loop. So as I said, you have an environment. The environment gives a state to the agent, and the agent selects an action. And this is trained via a reward that tells the agent how well the action taken perform in the environment. So the way I envision this is that the agent is like the brain that you want to train to learn the optimal actions. Okay. So this is our general pipeline of the process. So we start with the original circuit. We do its graph-like representation. So we can apply all the rules that we have. We fed this to the agent. The agent observes, the agent takes an action. After the action, we do a circuit extraction. So this is very costly to obtain the reward. That in our case, the reward is only the difference in gates before and after the action is applied. And we continue until the action stop is selected and we terminate the episode. And hopefully with the extract circuit, we have an optimized circuit. So this is basically what we're doing. Okay, so now, how do we use we use the Proximal Policy Optimization, the PPO algorithm to train our agent. There are a variety of training agents, training algorithms that you can do for reinforcement learning, but we use this because it's very robust and it has been shown that it's very powerful. How this algorithm works, it basically uses two functions to learn. One is the actor and the other is the critic. The actor, again, is the policy. The policy is only a probability distribution of actions for states. So the agent receives a state and needs to take an action. So and in the end is a probability distribution and selects the probability that selects the action that has a high probability and applies it. And the critic is a function that learns the agent, helps the agent to learn. And this is basically the quantity you should expect benefit from the current policy, but this only means that, so what are you getting or what I'm expecting to get? And the difference is something that I use to guide my training. Both functions are usually represented by a deep neural network. In our case, we use a graph neural network due to the symmetry of our problem. And these both functions, as graph neural networks, they have tunable parameters that are trained and optimized during training using a loss function. This loss function has three terms, one associated to the policy, one associated to the critic, and the other for the entropy. Very simply, I mean, the maths are difficult, but I just want you to get here intuition here, is that the policy loss is a quantity that ideally, not for policy gradient methods, are, as we just discussed with Max past week, but ideally decreases if the new policy selects better actions. So the agent at each point, if the action that is taken is giving better rewards, then the policy loss will decrease, in theory. And the value loss is, again, is this difference between what I'm getting or what I'm expecting. And if these two quantities are very close, then the value loss decreases, and then it means that the agent is slowly learning because it's currently it's easily predicting the result. And then we have the third term, which is very important, which is a term related to the entropy. And you notice that it has a minus sign. And this is because in reinforcement learning, you always want to balance exploitation versus exploration. Exploitation means when you have a good path that it's giving good rewards, you want to exploit it, but you also want to be able to explore new options, even if you are in the end of a path, because otherwise you're following a guided strategy and always choosing the best action that gives the better reward. So this term, it fights the policy and the value, and always it's compensating the loss function. So in the end, even if you're exploding, you will be exploring a little bit always. And well, this quantity is the entropy of the logits. The logits is the normalized probability distribution of the graph neural network outputs. Okay, so how do graph neural networks learn? A graph neural network has nodes and edges. I mean, a graph has nodes and edges, and each node and each edge has an state vector, that we say. And I'll explain what exactly our state vectors are in a minute. But first, let's say that imagine that xy is the node, right? And how do we update the state vector of xy? So we update it with the information of its past. So it's xyt. And so in the time t+1, we use xyt, so the past value of the state vector and its neighbors to update the value of the same node. This is done this is called a message passing layer. Obviously, if you add more message passing layers, you will at some point you will get that a node is getting information for all of its neighbors. So the information propagates from all the graph, which is exactly what we want, because otherwise all the neighbors would be influenced only by its nearest neighbors, and you wouldn't be able to correlate or grasp all the correlations in the diagram. Here the parameters are theta, theta s, and theta t, and these coefficients alpha and alpha yy and alpha ej are called attention coefficients. All of these parameters are just trainable parameters that the agent, by applying actions and getting rewards, will be optimizing, and at the end will be optimal and selecting good actions. Okay, so now it comes to I mentioned that the graph neural networks, it has nodes and edges. And so what structure do we choose? Okay, so imagine that we have a ZX diagram, which is something that what is displayed in the middle. We chose by symmetry to create both the critic and the actor to have the same connections and same nodes than the observation in this case, which is our ZX diagram. Why did we do this? It's arbitrary. There's an infinite of structures that you could try in reinforcement learning, and especially in graph neural networks. And we use this because it's one that performed best. So both the critic and the actor have these same nodes and connections, that is the text diagram, but now each node has a state vector. The state vector has 7 dimensions, and it has these. I'll explain now what the features of the state vector are. The first and the second feature are the sine and cosine of the phase of the node. So for example, here what I plotted, this would have the sinus of pi halves and the cosinus of pi halves, because it's associated to the node of the diagram, which is phase pi halves. And then we have 5 dimensions of one hot features, which means it's 0 or 1. And this helps the agent to understand whether another features, right? So for example, if the third element means that if the node is connected to an input or an output only. So if it's not, it's a 0, and if it's connected to an input and output, it's a 1. And then the other 4 nodes and for the actions. As you can see, every node is connected to an action. So the action nodes have itself a feature node, and with 1 or 0s depending on the action. So for example, the action LC will have all 0s, but in the 1 in the row of LC. Same with the stop, and same with pivoting, and same with identity. And okay, the other node that we can have is the node in the critic. As you can see in the critic, we don't have actions, so the node is 3-dimensional, only comparing with the phase, sine and cosine, and whether it's connected to an input or an output. And the last one is the node, the features of the edges. And the edges, it has 3 dimensions as well, and it's as well one hot, whether the edge is an edge that belongs to the ZX diagram. So if it exists on the ZX diagram, the second dimension is if the edge is a edge connecting a node with an action, and the third feature is to distinguish whether the edge is a node connecting action to an action. So as you can see, here we connect all actions between them and the nodes with the actions. This is just from trial and error. It's all very arbitrary. Like we don't know if this is the best structure or if this is the best policy, but as you will see the results later. But these scores, this can be improvable, and it just so we can the agent has more information about all what's happening in the diagram. Okay, so now we go to the experiments and results. So as I mentioned, we have two regimes in the Clifford simplification. The first one is for a small amount of gates. So to do that, to work on this regime, we trained our agent with 5 qubits and 25 gates, and the gates being the Hadamard, the S gate, and the C naught, with equal probability of generating all of them. And into results, our trained agent, we compare our trained agent and with the full reduce. So the full reduce in mean gets 27.7 gates, which is actually more than what we started, right? So this is not a simplification at all. And our agent, or in mean, gets 25.9 gates. But the most optimal agent, which means that what the agent that would be if it had a stop at the best reward syndrome in training, which usually doesn't happen, would get 25.5 gates. So what I meant to tell you by this is that we managed to outperform the reduce without the agent being the best version of itself. So you can always do more fine tuning of the agent and more indeed in-depth training, and that's what we have. That we hope it will happen. We didn't have time to do this, but it's something that we'll continue looking, and it's hopefully promising. And okay, so now what we did, we trained with 5 qubits and 25 gates. So first, okay, the good thing about graph networks is that they have a good generalization. So okay, how does this agent trained with 5 qubits and 25 gates generalize? So we have this same agent, and we compare it with the reduce for circuits of 10 qubits and up to 150 gates, which is a lot in scalability. And you can see here that we have two plots. The A is number of total gate counts, and B is 2 qubit gate counts. And we plot three things. The orange lines are the reinforcement learning ZX approach. If it is dotted, it means that we applied the algorithm basic optimization in the end, which is this gate-based optimizer that is it's implemented in the PyZX library. In purple, also dashed and not dashed, is the full reduce, and also the full reduce plus the basic optimization. And in the end, in blue is the what would happen if the agent took no action. So basically, you transform the diagram into graph-like, and then extract the circuit back from it. As you can see in the blue line, without performing the basic optimization in the end, it performs the worst, because obviously you are not applying any action. But after applying the basic optimization, it performs the best. And besides that, which is really puzzling, is that what the reinforcement learning manages to outperform the full reduce in both regimes, and I mean in this regime. And the good thing is that even though we didn't specify the CNOT count in our reward, the agent is able to learn these new strategies, as you see in plot B, that both without applying and with applying the basic optimization in the end, the reinforcement learning has better results than the full reduce. But still, nobody beats, no ZX calculus approach beats the transforming into graph-like, extracting, and then doing basic optimization. And we actually don't know why that is, but we believe that it seems like the basic optimization is done more than simplifying the original circuit and not the ZX diagram. The next test of scalability that we did is, well, now we did with 10 qubits and up to 150 gates. Now it's going to be 20 qubits and 350 gates. And here we compare our trained agent with high qubits and 25 gates with different versions of itself. In the first plot, you see the agent trained with 5 million steps against the same agent trained with 50K steps. And you can see that agent trained with 50K steps performs worse, and in a difference of 26 gates. The next agent is the same agent trained with 500K steps, and the difference is still significant with 12 gates. And finally, we assess this, we compare against the PyZX, and our agent manages to reduce 5 more gates in mean than the PyZX. And this is all good. I mean, if we think that this is an agent that has been trained with 5 qubits and 25 gates, that is able to generalize well for 20 qubits and up to 350 gates, but still it's not much. And well, it's this plot is for assessing the non-triviality of the policy learned, right? Because in the beginning, when the agent is not very good trained, in the beginning it's performing worse. But after training, which means that the agent has actually learned something that does better than the PyZX. Okay, now we go to the more challenging part, which is training our agent for the constant regime. Because obviously, if a basic optimization, if a classic optimization gate-based performs better than the static calculus approach, it's what we did is not very useful, right? So we wanted to go to the most challenging part and trying to train our agent in this regime. So for that, we use circuits of 5 qubits and 70 gates. And the results are, as you can see here, we have, again, 3 probability distributions. And in orange is the agent of trained with 5 qubits and 25 gates. In purple is the agent trained with 5 qubits and 70 gates. And in blue is the full reduce. So as you can see, the agent trained with 5 qubits and 25 gates performs the worst. So that is as well something. So the agent with 5 qubits and 25 gates, since it has been trained in the low gates regime, is not very good to generalize into the constant regime, which makes sense because we didn't train in that regime. But the agent trained in the high gate regime is, well, not by much as well, but by less than 1 gate, but performs better than the full reduce. And here it's especially difficult to balance the stop action, because how reinforcement learning works is, so the agent has all the actions and chooses one randomly. So in the beginning of the episode, if it selects the stop action, the episode will terminate and the agent won't have a lot of reward because no action has been applied. And you actually, with 70 gates, you have up to 20, 30 actions to apply. So what happens is the agent learns to apply all actions, so to up to 20. And when it's come to 20 actions, in the end, it's not able to apply the stop action, because all this process of applying all possible actions has been decreasing the probability of selecting the stop action. So in the end, what we need is to apply all actions, and in the end, after 2 or 3 more steps, and before finishing, to explore the stop action there. And this is what we said is this is difficult, because the probability distribution of all the actions, the stop will be lowering to 0 almost. So in the end, the agent won't select it. And that is why we believe this result is, so clearly the agent is getting a better, even though not that much, is getting a better order appliance than the full reduce, but since it's not stopping in the end, it's not performing that much. And with this result, with this trained agent, we again try to generalize it and see until how much it performs. And again, we try this agent trained with 5 qubits and 70 gates to test with circuits of 20 qubits and up to 450 gates. And here the full reduce, well, it does 404 gates, and our agent does approximately 403, so 1 gate less, more or less. Okay, so now what we did, right? We did, okay, so we have these 2 different regimes for small depth circuits and large depth Clifford circuits. And so we trained 2 agents, the 5 qubit and 25 gates and the 5 qubit and 70 gates. And we improved results in both, especially in the small depth circuit against the full reduce. And we assessed the generalizing capabilities, which is with the 5 from 5 qubits to 20 from 5 qubits to 20 gates. I'm sorry, from 5 qubits to 20 qubits with 350 for the small regime or 450 for the large regime. And the good thing is that even though we didn't specify in the reward, we managed to add a 2 qubit gates reduction in the smart regime, which is something that I think interesting. For I don't know if you have anything. Well, I we have future work, but I will prefer if you ask questions if you have. Otherwise, I can say future work because we've continued doing research about it. And then, yeah, well, that's what I meant here. We have future work and new ideas to discuss with you guys. But for now, thank you for your attention. And if you have any questions, I would be delighted to try to answer them.
Thank you. Does anyone have any question?
Yeah, I have a question.
Hello.
Go ahead, please.
Thanks for the talk. Did you guys think about non-Clifford circuits at all?
Yes, that's the future work discussion that I have. I mean, here. Yes. So this is implementable. Like it's not. And the thing is that we don't know much about the statistical calculus. I mean, we know what we learned during this work, but we didn't know anything beforehand. And yes, the main reason why we didn't try non-Clifford is because since we didn't have the best result yet for Clifford, so we believe because we programmed the genetic algorithm for the Clifford gates, and we saw the genetic perform gave the best result and the full reduce by actually 10 gates or something like that. So we know that this is improvable in the constant depth of the circuits. So we wanted to focus on that. But on a future work, yes, we want to go for non-Clifford, introducing phase gadgets. And here we have the work from John, and I believe some of you as well, of reducing T count. But it's different, right? Because here we would need, I mean, if we extract the circuit back from this structure, I don't know whether it would be good or we have good gates or less amount of gates. So that's why I believe in the paper reducing the T count, use this information to reduce the T count, not actually extracting the circuit. And that is what the full reduce is doing, right? They're extracting the circuit. But yes, it's something that we want to look at. We haven't, mainly because of this, because we haven't reached the best result in the constant regime of Clifford, and because we don't have more computational power. But it's obviously it's very interesting. It's more interesting the non-Clifford case because Cliffords are classically simulable, and yeah. But this is yes, it's in our mind.
I just had a comment about the Clifford case, which maybe you guys have realized as well, which is a random Clifford circuit.
Hmm?
Is pretty much on average always going to have quadratically many
Yes.
number of qubits. Particularly as you go to large numbers of qubits and large numbers of gates, I would expect basically any optimization procedure to land at about n squared gates. Because I guess the only variation then is kind of the exact single qubit gates that are happening at the inputs and the outputs.
Yes. Yeah. That's one of the reasons. I mean, in the beginning, we didn't even think if it was doable to improve on the full reduce in the constant regime. And if it's doable, I mean, we know it's doable now because even if it's 5 gates or 10 gates, which is not much if you have 450 gates, it's not much, let's be honest, but it is something. So yeah, that's we've been stuck with this for a long time, and yeah, we'll see what we do. But maybe it's just time to jump to non-Clifford and just drop the Clifford gates. We don't know. There's so many things we don't know about the calculus that it's puzzling sometimes. It's really puzzling that just the basic optimization performs better than all. It just doesn't make sense to us. Like obviously it's in the small regime, right? But in well, you know.
Yeah, I mean, my intuition there is if you have a circuit which is already generated by a small number of gates, then you're in this very sort of special part of the space, and they have a very sparse representation. So even though a random Clifford circuit is going to need order n squared gates, There could be, you know, if I take a circuit and I build it with 5 CNOT gates or something, then that's a very efficient solution to get that particular Clifford. And by the time you do the full reduce, you sort of forget that solution, right? So now you're in this big space of all the possible Cliffords, and then I just try to get an efficient representation of that, but it's almost impossible to find that very efficient representation that you started with.
I see.
That's kind of our sort of heuristic feeling of why this happens with full reduce.
Yeah, that makes a lot of sense. So I guess what we're trying to say is, or we thought in for the reinforcement learning is to guide, so the agent learns this guidance of the solution space, so it's always optimal, and in the end, the sequestration is just trivial. But that is very difficult to do, especially for, it's very difficult to write this because it sees a lot of stuff, and when you increase, or what we observe here, that when you increase the number of actions that the agent can do, it's very, very difficult to guide it efficiently. But yeah, that's a fair point. Thank you.
Thank you both. So we have an audience, Kaushik. He asked in the chat, how does the ZX calculus contribute to the effectiveness of the optimization process? Can this approach be generalized to other formats of quantum representation?
Okay, I believe, I don't think if I dare to answer this question in front of everyone, people that invented this calculus, but I would say that the good thing about if the effectiveness of the optimization process, well, if you manage to reduce the text diagram a lot by fusioning spiders and getting rid of some of them, and hopefully when you when you stack the circuit back from it, you will get less gates. I don't fully understand the question though. Maybe if some of you want to comment of it, please do it. I mean, I by no means claim to be an expert in this.
So while others are thinking about it, may I ask, just now you mentioned about this stop action, and you said this is very important for your reinforcement learning agent. How is this defined? And I saw that you use like a entry in the vector to define it. So what is that, like a binary value, like what that value is?
So the stop action, yes. So here you can see that the stop action is a node feature, which is 0 or 1. And this, the state vector of the stop action, which is, I mean, you don't see my pointer, I believe. But do you see the stop node in the diagram? Okay, so that node will be 0, 0, 0, 0, 0, 1, 0. That is how you codify it. And in the end, after all the message passing layers, this XY will be a lot of numbers in the features, right? So what we do to select the action is masking out all of our nodes, take only the feature vectors of this, or the state vector of the actions, and then running a softmax distribution, so you can get the probability of getting local complementation, identity, pivoting, or whatever. Did I answer your question?
Yes, thank you. And Max has a comment in the chat.
Yeah, Max, we are actually, I think we studied this paper in our work, so we are aware of that. But actually, I believe we started using neural networks not after, I believe after showing this paper, or maybe we're doing it and then we saw this paper. I don't know at which time it was published. Let me check. But I have it in mind. I read it. Yes, it was on the 17th of July. Yes, and I published my master thesis on September, so it was on when we started looking into graph networks, and then yes.
This was just meant as a comment to Kaushik's question, I think, because this could be another form of quantum circuit representation with a similar approach.
Okay, thank you, Max, for clarifying.
Do we have other questions?
I have a question.
Yes.
So it's during the training procedure, it seems that you appear to perform a circuit extraction on every iteration. Have I got that right?
Yes, definitely.
Okay, so that seems like obviously a very expensive procedure to perform. So you obviously highlighted that this idea that the point generalizes, because I think the hope there is that if we can train on a smaller number of qubits, but my question is sort of in two parts is, have you seen any limits on the scalability in terms of training on a small number of qubits and then applying to a large number? And my second point is there any way to develop a reward function that could work without having to extract the circuit? So you could perform the loop and it might scale to a larger number of qubits more efficiently.
Yeah. Thank you for your question. It's a very good one. Yes. Our results are for the maximum that our agent bits have produced. So for example, for the case of training of 5 qubits and 25 and 70 gates, up to more than 20 qubits, we start to lose, which makes sense because more than 20 qubits, the agent is a little bit lost on things have seen. So this is the scalability is up to 20 qubits for this trained agent. Obviously, you could try to train for 10 qubits agent or 20 qubits agent and then generalize to, I don't know, 40, 50, 100. The only reason why people don't do that is because, again, computational performance. And that's for the first part of the question. And the second part of the question is, yes, in the paper that I put in the beginning of my talk, which is from Corvina et al., they use heuristics to guide the process of simplification by assigning a cost to applying an action. So for example, applying local complementation has a certain cost, and applying pivoting has another certain cost. And then with symmetric annealing or greedy optimization or just random simplification, you can try to guide your simplification process. We could think of doing that. So we wouldn't have, for example, to extract the circuit back from it. Other rewards that could be thought of, or we thought of as, for example, would be the connectivity of the graph or other stuff. What we're doing now, and I'm sorry because I lost my screen, so I need to stop sharing and then share again. Okay, now I got recovered it. Let me quickly comment on what we're doing now, because I believe it's the interest of this audience. Okay, share. Okay, now keynote and play. Okay, are you seeing my screen? Good. Okay, so what we're doing now, something that I wanted to comment with you all is trying to, okay, so for example, when you have a ZX diagram, it's an undirected graph, but by using circuit extraction, you introduce directionality to your ZX diagram, right? So what we're trying to do is introduce as a feature of the state vector the cost of extracting a spider. So this means, for example, if a spider is in the frontier and it has a phase, so you infuse the phase, and that's a cost of 1. The other case is if there is a connection between nodes in the frontier, so that's CZ, and then you have we split the cost in 0.5, 0.5 for each node. Then you have the C nodes. The C nodes is the most difficult thing, and we don't know much how to associate this cost, because it's about this agency, this connectivity matrix, and then you do rows operations. And then depending on the operation, you have more or less nodes. So we don't know how to assign this cost to the nodes. What we're doing is, after the extraction, so we add 0.5 to each node of the C node connecting. But then we have another issue, that is that edges may appear in the circuit extraction process that you don't have in your original ZX diagram, precisely because of these agency matrix and row operations. So that